Okay, so in this questions, it gave us the Hamiltonian operator and asking for the matrix Hamiltonian. And also we need to find the eigenvalues and eigenvectors. So there is one rules that we can use for finding the matrix X. So the first step will be find matrix H. So the matrix H, I can write it in this form, H11, H12, H21, and H22. I'm just represent the columns and rows using the number. Okay, and if I want to find H11, I will just using 1 to sandwich the Hamiltonian operator, and the result will be H11. Okay, and if I do this, I will write the entire form. So I sandwich the entire Hamiltonians in the questions. Okay. Minus 2 plus 1. Oh, plus 1, 2 plus 2, 1. Okay. And now I need to distribute the sandwich to every small pieces into this parenthesis. Like this, like this, like this, like this. I will break them down. So now I have one sandwich, the one I have here. And of course, I need to multiply by the small e, the constant. And I sandwich the second term. I will get this multiply the small e and plus the third term, which is this one. One, one here, 2, and 1. Okay. And the last term. Oh no. Yes. Plus the last term. 1, 2, and 1, and 2. No, this is 1. Okay. And because in the question it says that 1 and 2 is two orthogonal bases, so this will give us 0, and this will give us 0, and this will give us 0. So the entire term is 0, 0, and 0. Okay, so now I have small e, because this will give us 1 because of the normalization. Okay, and if I apply the same idea to other terms like h12, h21, where is the h12, h21, h22, I will find that for h12, the only things that will give me the constant would be this one, because all the others would be 0, and you can try to do that, and you will find that the rest of the terms will just be 0. So now I find the only terms that will give me something is I sandwich the entire Hamiltonian. It would only be left with this terms. So now I have this. And of course, the small e. And this will be 1, this will be 1, so I have this. So h12 will be also the small e, And what about H21? H21 would be using the 2 and 1 to sandwich the Hamiltonian, and the only things that will give me at least something is the 2, 1. So the result will be small e. What about 2, 2? Well, the only things that will give me the constant is this term. Oops. This term. And it will be negative small e. Okay, so now I know that the Hamiltonian matrix is small e, this one, and negative e. Okay, and I can write it in this form, 1, 1, 1, negative 1. Okay, so now I already have the Hamiltonian matrix. I can start to solve for the eigenvalues. So let's write down the equation as phi is equals to E times phi, and this will be the eigenvalues. And this is the eigenstate, eigenfunction, and this one is the Hamiltonian matrix. Okay, so now this is what we have, and I assume the eigenstate is alpha and beta. Now it is equals to some eigenvalues E times the alpha and beta, and if I move this term to the left and combine them, I will have the determinant of phi minus, not phi, the small e minus the e, and I have this negative e minus, well, small e minus the big E. And equals to 0. I'm solving the E here. So determinant would be so the small e minus e and negative small e minus e minus the small e squared equals to 0. So now I need to solve this equation. So what do I have? I have minus square. So this is equals to minus this and this plus e. Yeah, this is better. And minus square minus e square minus square equals to 0. So now I have this 2e squared plus e squared equals to 0. So e squared is equals to 2 small e squared, and e will be equal to plus or negative 2 small e squared, which will be this. Okay. So now I have two eigenvalues. So now if we assume, so now we have actually two eigenvalues. The bigger one will be square root of 2, and the smaller one will be negative square root of 2. Okay. So now if we assume the eigenvalue is the bigger one, so now what do we have? We have this. I'm just copying the matrix. And this is the eigenfunctions, and this is the bigger one. Okay, and now we can use this to solve for the eigenstates, which will be eigenfunctions. It's just different names of it. Okay, and to solve this matrix, I have this plus this is equals to square root of 2 and this. Okay, and for the second line, I'm doing the second line right here. Minus this is equals to square root of 2. This. Okay, and if I cancel the small e, I forget the name of the small e, but I would just call it small e. Cancel out. Oh no, not this one. Cancel. So now I have this. And if I add this to, not actually add this two equation together. So the beta is equals to, I move this alpha to the right side. Okay. So now I already have my eigenfunctions, which would be for e plus, the eigenfunction would be alpha and square root of 2 minus 1 alpha. Because, so this is just beta, and I substitute the beta into this equation, so I have this. Okay, and it's the same idea for e minus. So phi for e minus, we have this equation, alpha beta equals to negative square root of 2 small e alpha beta. And now I have and if I cancel the small e, well, I will have alpha plus beta is equals to this, and alpha minus beta is equals to this. Okay, so the beta is actually equals to negative square root of 2 alpha plus, minus alpha. Okay, so this is my second relationship. So now the phi minus would be alpha and minus square root of 2 minus 1 alpha. Okay, so now I have this two eigenfunctions, the e plus corresponding to the phi plus and the phi minus corresponding to the e minus. So these and these are my eigenfunctions, eigenstates, and these two e would be the eigenvalues. So this kind of question is very common in this chapter, and you might see some 3x3 matrix version of this kind of problems, but solving the eigenvalues, solving for the eigenstates, eigenfunctions will be very common, and you will see them multiple times in this chapter. So it's very useful.